Tokyo awakens before sunrise. Beneath its streets, engineers carve a cavern, wailed still in the dark, and ask the ground itself to bear a tower. That hidden labor is the prologue to Toranomon Hill Station Tower, a 266-meter test of what a dense city can build when it refuses to wait for open sky. This week, we intend to examine the construction from the underground of Toranomon Hill Station Tower to the above-ground tower structure. In week 3, we mentioned that, taking into account the ground environment beneath Toranomon Hills, the presence of soft ground, and the technological situation in Japan, the retaining wall was not built with sheet piles, soldier pilagging, or a diaphragm wall, but rather with the SCW method. While excavating the soil, we simultaneously carried out the SPS top-down method, which provides many advantages to Toranomon Hill Station Tower. When the top-down method is executed with steel members, it is generally divided into the STD method and the SPS method. In the conventional strut top-down method, temporary struts are installed during the excavation stage to support the retaining wall. And after the underground structure is completed, these struts are removed. However, this process entails stress imbalance, damage to the structure, delays in the schedule, and the risk inherent in dismantling work. In contrast, the strut as permanent system method makes use of steel members that will be employed as the building's permanent structure members from the outset instead of removing the temporary struts. During excavation, they function as members resisting lateral earth pressure, and after the structure is completed, the same members continue to act as horizontal members of the building. Therefore, the difference between the two methods lies in whether the structural member is integrated into the permanent structure of the building or dismantled as a mere temporary member. In the case of Toranomon Hill Station Tower, the SPS method eliminates the process of removing temporary struts, thereby reducing the overall construction period, and it has the advantage of effectively reducing structural crackling and ground deformation even under soft ground conditions. This method first begins excavation to the depth of basement level 1, based on the retaining wall created by the SCW method. After that, brackets are installed on the SCW wall to form a support base for structural members, and along these brackets, a perimeter girder called a wale is installed. The wale is a horizontal member that disperses the earth pressure acting on the retaining wall and plays a key role in the structure together with the main struts that will be installed later. The main struts installed thereafter are not temporary, but permanent steel members that will be used as girders in the actual building. These steel girders support each earth pressure during excavation, and when slab and wall construction follows, are converted into permanent structural members. This process is repeated for basement level 2, basement level 3, and below. And at each level, the brackets, wale, and main struts are installed in the same manner, followed by the construction of slabs and internal walls. When excavation to the lowest basement level and installation of the structure are complete, the base mat slab is constructed, and at the same time, interior retaining walls and slabs are built from the bottom upward. In particular, in the SPS method, the up-up technique, which constructs the upper ground and underground portions simultaneously, is applied so that the construction of the underground floors proceeds in parallel with the erection of the above ground frame. This SPS method thus secures both structural stability and construction efficiency even in a complex and confined urban underground environment, and can be regarded as a very advanced solution for underground construction in modern super tall buildings. With the commencement of underground work using the top-down method, 58 of the 182 columns in the basement were extended upward, making it possible to construct the tower above ground. Steel members are integrally connected to the CFT columns by on-site welding as they rise. The steelwork of Tournament Hill Station Tower erects columns and beams such as H-shaped or box-shaped sections, and units of 4 stories called a tier assembles the floor deck, and then erects the next steel frame above. Because of the curing period of the high-strength concrete in the CFT columns and the lifting time of the steel members, one tier takes 28 days. The sequence of one tier is as follows. Steel members are prefabricated in the factory, transported to the site, and lifted by 4 large tower cranes installed on the perimeter. The lifted steel members are then welded. Next, deck plates are installed. After that, concrete is placed inside the CFT steel tubes, and curing is carried out by covering them with curing blankets. These operations are repeated as the stories rise. The slab is constructed by installing deck plates on the steel girders, then placing reinforcing bars and field casting concrete. The construction procedure is as follows. Reinforcing bars are laid and shear connectors are welded on the deck plates fixed on the steel girders. Concrete is then poured, and finally surface finishing and curing are carried out, whereas the steelwork that produces one tier takes about 1 month. The process of placing reinforcement and casting concrete for one floor slab takes about 10 days. Therefore, the slab casting process proceeds more slowly than the steel work. In addition, because slab casting was carried out after equipment installation at Tournament Hill Station Tower, concrete had to be poured long after the steel work had proceeded according to the flow line schedule. To cast the slabs inside the limited space where all the steel frame had already been erected, vertical piping and the pumping method was used. In this method, vertical pipes are installed inside the core and the concrete is pumped. In a super tall building such as Tournament Hills, concrete pumping performance is important and is related to the flowability of concrete, the length over which concrete is pumped, and the efficiency of the pump. For concrete with a slump flow generally greater than 600 millimeters, a pressure of approximately 0.3 bar is applied for every 1 meter increase in height. Thereafter, concrete is pumped by adjusting the pump pressure according to the flowability of the concrete as determined by its strength and the delivery height. In this way, the steelwork advances in units of 1 tier, the slab casting advances at a rate of about 1 floor every 10 days, and the super tall station tower is completed. However, station tower did not carry out this procedure in the same manner on every floor. To realize its unique shape and spatial composition, Tournament Hill Station Tower strategically selected and applied various types of steel to each structural part. The main steel grades used were SN490C, TMCP325C, and TMCP355C, and these were appropriately arranged according to the characteristics of each structural part. SN490C is a rolled steel for buildings with a tensile strength of 490 megapascals and is therefore used in parts subject to large tensile stresses. TMCP steel is a high-strength structural material manufactured by thermomechanical control process rolling. It requires no or minimal preheating during welding and maintains excellent toughness even in the heat-affected zone of welds. Because TMCP is advantageous for welding in this respect, TMCP was used mainly in structural parts with a large amount of welding, and the relatively inexpensive SN490C was used for other members. In the floors where building services piping is concentrated or structural transformation occurs, namely floors M10, M14, and M44, and in the lower level, skybox, MEP box, and activity band, long span trusses, Y-shaped merging columns, and V-shaped columns were used. These structures involve many locations with large spans and concentrated stresses. Accordingly, SN490C, which has the characteristics of high strength and high ductility, was used for most of the steel. In addition, the on-site welding rods were fabricated from TMCP steel, making it possible to achieve high-quality welding without preheating even in thick knots. From the first SCW bite to the last rooftop weld, Tournament Hill Station Tower pressed every square meter of Tokyo to earn its height. It fused top-down speed with permanent struts, pumped concrete a quarter-kilometer high, and stitched 3 grades of steel into one seamless skeleton. In a crowded city, engineering is not just problem-solving, it is high-stakes choreography. And when the curtain lifts, the tower itself takes the bow.